Hello there. Solution video to problem set number 13, where we take a closer look at kernels and images of homomorphisms. Exercise 1 is simply to prove, it's not A, it's 1. If phi, I'm a bit confused about the pronunciation in the Greek letter phi, in German is pronounced phi, in English I would suppose phi, but the other day I heard someone pronounce it phi, so please comment below. In this video I'm going to call it phi. Phi is a homomorphism between groups G and H, a group homomorphism, and then automatically its kernel is a subgroup of G. This is the first thing we are going to prove. So we abbreviate the kernel by capital K. We're using the condensed subgroup criterion, so first of all we have to convince ourselves that this is not the empty set, but we know from problem set 11 that a homomorphism always maps identities to identities, so E sub G gets mapped to E sub H, and this exactly means that E sub G lies in the kernel of phi, so the kernel is not empty. Next we take two arbitrary elements of K. G and H is maybe not such a good choice of notation because here we have the groups G and H, so I call them A and B. But this simply means that both get mapped to the identity of H, and we have to show that then AB inverse also is an element of K. But with our knowledge of homomorphisms, this is easy because phi of A times B inverse is the same as phi A dot phi B inverse. Now this dot is the operation in H. This is just the homomorphism property. And now by exercise so-and-so on problem set 11, I think it was the first one, we know that this here is the same as this. But then this clearly gives the identity of H because the neutral element is inverse to itself. And this shows that if both lie in K, then also this product A dot B inverse lies in the kernel because it gets mapped to the identity. And now, citing the condensed subgroup criterion, we know that K is a subgroup. You should write down here what I just said. Okay, next we have to show that also the image of phi is a subgroup. Then of course not of G, but of H, because by definition I abbreviate it with capital I. I consists of all these elements, phi of G, G running through the whole group G, so this is clearly a subset of H. And again, we're using the condensed subgroup criterion. So clearly the image is not empty because at least phi of EG is in the image. No matter what the group G is, it definitely has a neutral element, an identity, even if it's the trivial group. So the image is not empty. Next, we take two arbitrary elements of this subset. And now by the definition of the image, X and Y can be written like that. X is phi of A, Y is phi of B for some suitable elements of G. This means exactly lying in the image. And now all that is left to show is that then this here lies again in capital I, X dot Y inverse. But now we're using this. It's the same as the proof for the kernel, only in the other direction. We know that here I can pull this inside. We prove this for every homomorphism. And now, because phi is a homomorphism, I can write this like that. And this here is clearly an element of G, so this here lies in the image, thus finishing the proof. So by the condensed subgroup criterion, we have established that the image is always a subgroup of H. Okay, next statement. This is very important. It states that the homomorphism phi is injective if and only if its kernel is trivial, meaning it consists only of the identity of G. Let's do this separately for both directions. So first of all, we assume that phi is injective, and then we show that its kernel is trivial. So we take an element of the kernel, then we know that phi of x is the neutral element of H, but we already know that this is always true, that phi applied to EG is always EH for any homomorphism. And now if I compare those two and know that phi is injective, this leaves only the possibility that x is already the neutral element of G. Yeah, here by definition of injectivity, if this is true, then it follows that those elements here already must be the same. So this proves that the kernel consists only of the neutral element of G. And sorry, I have no idea why I call this element x to be consistent with the solution before. I should call it G or A because x and y were elements in H in part 1. But whatever, you have to be a bit flexible with notation, but this was not a very good choice. So we assume that the kernel is trivial, and we need to show that phi is injective. So we assume that phi of A is phi of B. And we need to show that from this it follows that A is equal to B. Now I can multiply this equation from the right with the inverse of this element in H. This is always possible. I'm in a group. So on this side I end up with the neutral element of H, and on that side I end up with this. And now by the same argument as before, I can pull the -1 inside, and because phi is a homomorphism, I end up with this. Okay, but this exactly means by definition that AB inverse lies in the kernel of phi because it gets mapped to the neutral element of H. But now by assumption this kernel is trivial, so that leaves only the possibility that this here is already the neutral element. Okay, but now multiplying from the right with B gives me A equals B, so we see that from this here it follows that. And it would have been enough to always write the arrows in this direction because I want to go from here to there. And this shows that phi is injective. Okay, if you could do that on your own, as always, and if you're a beginner, please comment below. Would be very happy if you're already at that stage of abstraction that this is doable for you. And if not, don't feel bad. Give yourself some time. It will get easier and better once you get more acquainted. Okay, now statement 3, as I already said in the video for the lesson. This by definition means that phi is surjective, so there's nothing left to prove here. If the image is all of the codomain H, then the map, be it a homomorphism or not, is surjective, so nothing to prove here. So this concludes exercise 1, the proof of proposition 16. All right, exercise number 2. Phi is a homomorphism from G to H. J is a subgroup of H. Then automatically the pre-image of J is a subgroup of G. And again, a word of caution or warning. This does not mean, this notation, that phi is bijective and has an inverse homomorphism, but this is simply the notation for the pre-image. I can write that down for any map, especially for a homomorphism, but it need not be bijective. So this is simply the set of all elements in G, in the domain, such that they get sent to J in the codomain H. This is simply a set. And now we need to show that this is a subgroup. Now, before I forget it, this is a generalization of exercise 1, part 1, or proposition 16, part 1. if I set J to be the singleton set consisting only of the identity of H, then by definition the kernel of phi is the pre-image of this set, or in other words the fiber of EH. And we already showed there that this is a subgroup. Now this is the generalization. So if you notice that, you could also say see exercise 2 and set J to be the set consisting only of EH. Then you would have proved this here as well. And the proof is pretty similar. Okay, to ease the notation, we abbreviate this here with capital P. And first we need to show that this here is not the empty set. And for this we already need that J is a subgroup, because as a subgroup it must contain the identity of H, and we know that every homomorphism maps the identity of G to the identity of H. So we use both facts, first that phi is a homomorphism and that J as a subgroup must contain the identity. And this here by definition means that EG is an element of this set, because this is exactly what happens. If I map it with phi, I end up in J. So next we take two arbitrary elements of P, and that means exactly by definition of P that the images under phi lie in J. Now it's the same argument all over again. I look at A, B inverse, map that with phi, and because phi is a homomorphism, I can write it like so and pull the -1 outside. And now we know by definition this here is in J. Phi of B is in J, but then also its inverse is in J, because J is a subgroup. So with an element it also contains its inverse. Please write that down here if you're taking notes. So here we use the fact that J is a subgroup. Maybe write it like that. And again, because J is a subgroup, the product of two elements that lie in J again lies in J. So here we twice use the fact that J is a subgroup. But if phi maps this guy into J, this by definition means that this element here is an element of P, the pre-image of J under phi. And using the condensed subgroup criterion, we see that this proves P is indeed a subgroup of G. So, and that's a good thing to remember. Whenever I take the pre-image of a subgroup, I pull it back to my domain group, then it stays a subgroup. That's useful in a lot of instances. And I'm saying this over and over again. I do not always write the complete sentences on the blackboard here, but if you strive for a perfect solution, then always write down a little more text than I do here. For example, here, you could write that in words, or here. Please train to do so. Okay, next exercise. We need to determine kernel and image for a list of homomorphisms that we studied in another problem set. We start by the squaring map, which sends a group element to its square. So G times G, which is clearly again element of the group G. What is the kernel? By definition, all the elements that get mapped to the identity of the codomain, which is the same as the domain here, so the identity of G. And this exactly means these are all the elements of order 2 or the identity. The identity itself has order 1 because it is already to the power of 1, the identity. And the other elements that are not the identity and fulfill this have by definition order 2. So the kernel consists of all elements of order 2 together with the identity. The image is by definition the set of all these guys here, phi of G, where G runs through the group. So the set of all G squared, where G runs through the group. If this helps you, you could call those elements the elements that have a square root, because G then clearly is the square root of this element, because the element can be written as G squared. I do not find this particularly useful, this terminology. Think of the Klein 4 group, for example, then this whole set collapses to the identity Or in other words, the identity has different square roots, namely all the elements of the Klein 4 group, because they all satisfy that this here squared is the identity. So in this case, the kernel would be the image. Okay, next, the good old exponential function, which, as we established, is a group homomorphism from the real numbers together with addition to the positive real numbers together with multiplication, because e to the x plus y is the same as e to the x times e to the y. Now, what is the kernel of this map? By definition, all real numbers that get mapped to the neutral element here, which is the real number 1. And this clearly is the only real number that satisfies this, because the exponential function is streng monoton steigend. A strictly increasing function, I think, is the correct terminology. And now we know from proposition 16 that this means that X as a group homomorphism is injective, as should be obvious from looking at the graph. We already know that about the exponential function, but here in a new light we can say because the kernel is trivial, we have an injective group homomorphism. Now, what is the image? The image is simply the set of all these guys here, e to the x, where x runs through the real numbers. And now we take this from analysis or calculus or whatever you want to call it, that this is indeed the whole codomain. So we have a surjective homomorphism. Of course, we're not going to prove this here. This is a course on abstract algebra. Okay, next we established that this is a homomorphism from a field to this subset of the general linear group over F, consisting of these matrices here. The matrix of this form I call A sub small a. And a field element simply gets mapped to this matrix. Now, what is the kernel? By definition, it consists of all the field elements that get mapped to the identity of this group, which is clearly the identity matrix, but then it's evident that only 0 fulfills this requirement, so the kernel is trivial and we have an injective homomorphism, which should be self-evident even without looking at the kernel, because, yeah, just look at that. If you understood injectivity, then you see with one glance that the kernel, that this map is injective. And by definition, it is surjective because H consists exactly of these matrices, so the image trivially is H. So this is what we call an isomorphism. It's a group homomorphism that is injective as well as surjective. So we have a one-to-one correspondence between these groups, the additive group of the field and the multiplicative group consisting of these matrices here. Okay, part D. We fix an element G in a group, a capital G, and we send an integer to the kth power of G. Then we establish that this is a homomorphism. Now let's find out what the kernel and the image look like. So by definition, the kernel consists of all integers that get mapped to the identity. So phi, or the phi of G is G to the K. This must be the identity. But now this means, remember, we proved that some weeks back, if G to the K is the identity, then the order of G is, if and only if, the order of G is a divisor of K. So these here are all the integer multiples of the order of G. So I could write this like that. We take the order of G times Z. Let's look at an example to make this more clear. If, say, the order of G is 2, so G is not the identity, but G squared is, then the kernel, by this observation here, is 2 times Z. And indeed, if I raise this G to the power of 2 or 4 or 6 or any even number, I end up with the identity. And also because g to the minus 2 is g squared inverse, which is E inverse, which is E, also the negative even numbers give me... Oh, I scratched the blackboard with my nail. Ah, I'm sorry, a horrible sound. So even the negative even integers give me the identity. So in this case, this would be 2z. That's, I think, the first interesting example of the kernel of these homomorphisms. Now, the image of phi sub g consists by definition of all phi g of k, so all the powers g to the k, where k runs through the integers. And by definition, this is nothing else than the cyclic group generated by g. This is exactly that, which can be quite small. In this example here, it would simply consist of E, the neutral element, and G itself. So that was an interesting example of kernel and image of a homomorphism. Okay, and finally we take a look at this rather abstract or even more abstract map that we discussed at the end of problem set 12. Lambda from a group to the symmetric group on G, consisting of all the bijective maps from G to itself, sending a group element to its left translation, meaning that LG applied to a group element H is simply G dot H, dot the operation in the group. Now, what is the kernel of this map? By definition, it consists of all elements here that get mapped to the neutral element here, but this is the identity. The identical map is a bijective map, which is the neutral element with respect to composition. But now think about it. When is this map here the identity? If and only if it does nothing to all the h's. So what is the only group element that does nothing when multiplied from the left? Well, clearly this is only the identity. Only the identity can fulfill this. Maybe here again this argument. When is L sub g, which is nothing but lambda of g, the identity of g? By definition, if for all group elements H, this here, LG applied to H, is the same as H, only then it is the identical map. Then we can cancel the H and we end up with G equals E sub G. This would already suffice if it holds for one element. So the kernel is trivial, so this map is actually an injection. Sometimes you see it written like that, or maybe like that. Yeah, it doesn't matter now. This is an injective map from the group into this set here. Now, what is the image? The image consists of all left translations, where G runs through the whole group. Can this be all of this group? We don't really understand that group that well. But let's take, for example, a finite group of order n. Then this clearly consists of n different elements, because for each different element this yields a different map, because it does something else to the neutral element, for example. So all these maps here are different. Yeah, apply this to the neutral element, you end up with G. And if G is not equal to G prime, then those maps do not agree on the identity, so they are not the same map. So the image consists of n elements, these here. Let's exclude the two trivial cases where this group has one or two elements. So for n greater than or equal to 3, n is strictly less than n factorial, which is the order of the permutation group of degree n. And we established in the exercise back then that this is the same up to isomorphism as the symmetric group on G. So for n greater than or equal to 3, this here cannot be an epimorphism because the image is smaller than the domain. Okay, we have already arrived at the final exercise of this nice little manageable problem set 13. So we take as our domain the group consisting of all the vectors in the Euclidean plane, x, y, together with component-wise addition, as you know well from high school. And our domain consists simply of the real line, which can be interpreted as this subset of G itself. So, and pi is nothing but the projection onto the x-axis. That is the geometrical meaning, because we send such an element to its first component, meaning exactly what I just said. We project parallel to the y-axis this point here down. So, but opposed to high school, I write my vectors here without these little arrows above them, but simply as v and w. So we need to show that pi is a group homomorphism, component-wise addition and normal addition being the group operations. So let's take a look at that. So that I do not run out of letters, let's call these vectors here, these elements of this group, v and v prime. And we do not write them in column vectors as we used from high school, but like that, because this agrees with the notation of the direct product of groups that we studied on problem set 4. So now this here is addition in the group G. And what does component-wise addition mean? Exactly that. We add the x component, so we have that, and we add the y component, so we have that here. And now what does pi do? Pi projects onto the first coordinate, so this here gets sent to x plus x prime, but this clearly is pi of v, because if I map this here, I end up with x plus pi of v prime, and this now is addition. And this now is addition of real numbers because we are in the codomain H. So this clearly shows, this is true for all v prime in G, establishing that pi actually is a homomorphism. It's the projection homomorphism onto the first coordinate. Okay, and in B we're supposed to find kernel and image of this map. And again, this has a nice geometrical interpretation. By definition, the kernel of this group homomorphism consists of all elements of G, so of all vectors in the Euclidean plane, such that they get mapped to the neutral element here, which is simply the number 0. And this is pi of this element here. Pi of this is exactly x. So this is simply this set of vectors. First component is 0, second component is any real number. So we get the complete y-axis as the kernel. And now if you look at that and think about pi as projecting downwards, then you clearly see every element here. So every vector or every point on here, whichever way you want to interpret it, gets mapped to this 0 here. So that's a very nice geometrical example to think about a kernel. So this shows that pi clearly is not injective, it's not a monomorphism, because all these elements get mapped to the same element, or because the kernel is highly non-trivial because it consists of infinitely many elements. Now what is the image? Clearly the image is the whole x-axis. Why? Because if I take any number here, I can take this x0 as a pre-image, or I can take this arrow or whatever I want to. I can add the whole kernel, so the whole y-axis, to this element here and have infinitely many pre-images. So clearly it is an epimorphism because its image is all of the codomain. And again, because it's so nice to think about this geometrically here, the fiber of this element is simply this point here with a parallel line to the y-axis. All these elements here get mapped to x. So the fibers are all parallel lines to the y-axis. All right, this concludes problem set number 13. I hope that was enjoyable for you and doable and didn't take as many hours as problem set 12. All right, hope to see you all in next week's lesson where we talk a bit more about the concept of isomorphism.